Hi, this is chapter 5, which discusses the memory hierarchy. And before we get into this chapter, let me do just a quick introduction on the whiteboard here. Basically, what we have is the CPU, which is fast processor, interacts with the memory system. Okay, and we would like to have as large memory as we can. Okay, as large memory as we can. So obviously, this was the architecture in early systems, but what happened? What happened? Um, People realized very quickly that there is really a mismatch between the speed of the CPU and the speed of the memory system. But we need the memory system to be large as we can, so we can fit as many programs and as many functions as we can. So people came up with this hierarchy system. And this hierarchy system says that we have here the CPU, right? And we have sort of like this memory subsystem is almost like a pyramid where you have here on the top the registers, uh, part of the CPU, and then you have caches, and then you have main memory, and then you have hard disk or hard drive. Okay, and you can have other levels, but I'll stop here. And the concept here is that you will see that the on top of the pyramid here, you have the memory are small and fast when you go to the top of the pyramid. While we go to the bottom of the pyramid, then the memory becomes large and slow. One thing important also is that the memory on top here, that the cost per bit is high, while the memory at the bottom here, the cost per bit is low. So the idea is to have fast memory closer to the CPU so that the CPU interacts with this fast memory. Okay, so the memory reservoir is your hard disk here. So the question that comes in mind here, what do you have in these higher levels? Well, what you have, the main memory will have a copy of a subset of the hard drive. It cannot have the entire hard drive because the memory is smaller in size. And the cache will have a copy of subset of the main memory. Okay, so what is the question is obviously what to copy. The memory is less than the hard drive, and the caches are smaller than the memory. What to copy? What to copy? And this is really governed by two principles. And these principles help me to copy what I want or the maximize the benefit of copying. The first principle is called temporal locality. And the temporal locality basically it says items that are accessed in the memory or lower levels they have been accessed recently, they are likely to be accessed again in the future. So examples for that, instructions in a loop, because this loop iterates and we're going to repeat fetching those instructions again and again and again. So it helps to keep those items accessed recently in main memory and copy them in the cache. That's the temporal locality. So that's a big hint here. And the other big hint is the spatial locality. And the spatial locality basically says that items in a lower level of memory access or items in memory, I should say, restate this, items near those accessed recently, notice the word near, items near those accessed recently are likely to be accessed soon. Okay, that's good. The good hint. Which means if I'm accessing an array, it's good to copy it on the. So if I'm accessing an array, it's good to copy this array to cache. If I'm if I'm accessing instructions, I know if I'm accessing the current instruction, the following instruction will be accessed soon. So that's so temporal locality says items accessed in memory will be accessed again in the future, and their neighbors will be accessed as well, and that's the spatial locality. Okay, so that helps me narrow down the smaller list of items that I need to copy into cache. Now let's go to the lecture. Okay, and see from there. So obviously in this lecture we start by introducing the different technologies: static RAM, dynamic RAM. So obviously we would like to have the best speed of memory, which provided by static RAM, but obviously static RAM is dominant in implementing registers and caches, and the DRAMs are for memory because of their density. DRAMs are very dense, static RAM are faster. And obviously these are the two principles that we have discussed here, which helps me to copy a subset of the lower level to the upper level. Lower meaning, or for example, the main memory. The upper level, for example, the cache. Now, so here, if we see here, this is the processor, and this is here the cache, and this is here the main memory. Okay, and notice that data is transferred between the processor and the cache, and then data is transferred between the cache and main memory. But here the processor and the cache, it is transferred by word size, and we can have half word or byte. But but between the cache and the memory, they are transferred by the block. And the block consists of one or more words. So this is a block which consists of 4 words, for instance. It can consist of 8 words or 16 words, or etc. etc. Okay, so this is the unit of copying between cache and memory. If we access a data and we find it in the cache, we say that we were successful, and this is a hit. And if we don't find it, we say that this cache we were unsuccessful to find the data, then it is a miss. So if we have, let's say, 100 accesses to the cache, and we found out 90 successfully, 90 of those, and 10% of or 10 of those items are not there. So we say that we have a hit of 90 over 100, which is equal 90% hit rate. And we missed 10 out of the 100 items, so we have 10% miss rate. Okay, so obviously miss rate and hit rate, miss rate plus hit rate equals 1. Okay, all right, so that's okay. So whenever we have a miss rate, we'll see later on that or a miss, we will see that we'll have to pay a miss penalty. We'll discuss obviously later in the chapter. Okay, and we have here two important policies for the cache, which is the placement policy and replacement policy. So basically, when I have, so this is the cache, right? And oops, so this is the cache, and this is main memory. So when I bring a block here, the question is where to place the block. Okay, so where to place the block in the cash is the placement policy, determined by the placement policy. Replacement policy says, replacement policy says, when the cache is full, this is full, and I need to discard one of those existing blocks, I need to discard it. Which one I discard? Okay, why do I discard it? Because I want to make a place for a newcomer from the memory, a new coming block from the memory. So if I want to discard it, which I should discard? That's the replacement policy. So the placement determines where I place the block in the cache. Replacement says which block I discard. These are two important policies for the cache, and we'll start with the placement policy. And I'm gonna go through over an example on the whiteboard here so that we can because I don't like the way they are explained in your slides, so that we can understand better what we are talking about in these policies, and we will explain those policies in the next part of these lectures. Thank you.